Was soll ich denn sagen? We start. All technical problems have been solved?
Nope. Okay.
Again, all technical problems have been solved, hopefully. Again, all technical problems. Good. Okay, good. Then let's start. So today we start with the cryptography part. But let me briefly remind you of lattices and lattice problems. So lattices, additive subgroups of R to the n that are discrete. And then this is an example, and then we saw that what we can always find for lattices are so-called bases. So lattices, alternatively, are sets of integer linear combinations of R linearly independent vectors. But that doesn't necessarily mean that these things, that bases are unique. In fact, they usually are, they never are unique. And in fact, there are usually infinitely many of them. The way we can relate bases to one another is by unimodular matrices. And we also defined the fundamental parallelepipeds for lattices here, although this is not the origin-centered, but it's the 0,1 parallelepiped. And we have lattice bases. We have seen that there are good ones and there are bad ones. There are actually ways to quantify this, but I won't go into the details here. And then we looked at several lattice problems, namely the shortest vector problem, SVP, where we have to find a shortest non-zero vector in a lattice. These things are also not unique, although sometimes I will certainly say the shortest non-zero vector in a lattice, which is always wrong, but never mind. If you know that it's always wrong, then you can correct it yourself. That's easy. And then you have the approximate shortest vector problem, where we are not asked to find the shortest vector, lattice vector, but one that's almost shortest up to a factor of gamma of n in the length. And the decisional approximate version of it, where we have to, we are given a lattice and we have the guarantee that either the lattice length is at most 1 or it's at least gamma n, and then we have to decide in which case we are. 1 is obviously arbitrary. You can, by scaling, you can replace that by any other thing. Then we had the approximate shortest independent vector problem, where we are asked to find n linearly independent lattice vectors whose length is at most gamma n times lambda n of L, where lambda n of L guarantees that these things are always exist. Okay. And then we have finally the bounded distance decoding problem, where we are given a basis of a lattice and a target T with a guarantee that the distance of the point to the lattice, so the nearest point to the target, the distance lies, that the distance is, is at most d, and d is lambda 1 of L divided by 2 times gamma of n. Gamma of n is always at least 1, and just this 2 guarantees that in this case, with that guarantee, the closest vector is actually unique. If it was not, then lambda n could not be correct. So again, we are guaranteed here that the distance of the point to the lattice is rather short. Okay, so short that it's actually unique, and then the gamma n even makes it a little bit better. So if we increase gamma n, then we make the problem easier, as usual, because then the point gets closer and closer to, or guarantee is that it's closer and closer to the lattice. Eventually, it's so close that it is a lattice point. Okay, all of these problems we don't know how to solve efficiently. The best known algorithms have a runtime that's roughly 2 to the n. The important parameter here is the lattice rank. All these things can be made polynomial in the size of the numbers in the basis. That's not a problem. This is slightly below 2 to the n because of this log n divided by log n. That's okay. If you want, this is for the approximation problems. If you want exact algorithms, then you either have to spend time 2 to the n log n or have single exponential time n space. These have polynomial space. And there are actually, that's the important observation for post-quantum cryptography. There are no significantly better quantum algorithms for these lattice problems. On the negative side, so the hardness of these problems, all these problems are NP hard for approximation factors n to the little o of 1. And this little o is 1 over log n. So that goes to 0 as n goes to infinity. That's true at least. Yeah, that's true for all of them. These essays are written down here. But they are not necessarily NP hard, or probably not NP hard, for approximation factors above square root of n. Square root of n is larger than this here. Square root of n is 2 to the log n divided by 2, whereas here we have 2 to the log n divided by log n. So the denominator is larger. This here, if they were NP hard for larger approximation factors, then depending on what gamma n you are talking about for square root of n, you know that the polynomial time hierarchy collapses to its second level. If it's even for square root n divided by log n, it's even that np is equal to co-np, which we do not believe. Unfortunately, all the lattice-based cryptographic constructions that exist today need for their security the assumption that the certain lattice problems are hard for approximation factors at least n. So they fall into this regime. So we cannot base the security on NP hardness, but there is lots of things between polynomial time and NP hardness, probably. Unless they collapse, polynomial time and NP hard problems are the same, then there is an infinite hierarchy between the two. Okay, so most people believe that even for those factors, it should be relatively difficult, even for quantum computers, to solve these problems. Okay. Okay. Good. But the modern versions of cryptographic primitives based on lattices are not based on SVP or SIVP or BDD, but they are based on easier to describe, more combinatorial versions of lattice problems that I'm going to describe next. Okay? And that's the new part now today. So here is the first one. It's called the short integer solutions problem, or the two things that we look at are the short integer solution problem and the learning with error problems. So they are the two most important ones, but they can be related to the hardness of SVP and SIVP. And in particular, the last one, LWE, is very powerful. Okay. Then what we also can do is I will only present those things in the general lattice setting. There are constructions where you look at specific classes of lattices. These are the so-called ring variants of these problems. They lead to the currently most efficient lattice-based cryptographic constructions, but I won't talk about them. And we won't talk about them in the seminar at all. In the seminar? Not in the seminar. So that's what I said. I didn't say that I will never talk about these things, but in the seminar we are not going to talk about these ring variants because they require additional mathematical structures. But in this sense, in these variants, the ring variants, these are the basis for various candidates in the competition for post-quantum standards for encryption and signature schemes that is currently underway by the National Institute for Standards and Technology in the United States, and we're currently in the third round. There are 4 signature schemes. I think there are 4 candidates left. 2 are based on lattices, 1 is based on coding theory, and 1 is based on so-called multivariate polynomials. But coding theory is it's quite close actually to lattices. Okay, let's go to the short integer solution problem, SIS. It's parametrized by 4 parameters, n, m, q, and beta. M here is often not so important because it's fixed by n and q basically. And n and q together define the group zq to the n, so everything's modulo q, and we have vectors of length n. And beta is a norm bound, and m is sort of the number of group elements in zq to the n that we are looking at. Okay. What is the role of these group elements? What do we do? So here is the definition of the short integer solution problem, SIS NQ beta n. Okay. M is at the last on the list because that's the least important one. Actually, it usually can be deduced from the other ones, as I will explain. So here it is. Given m uniformly random vectors ai in zq to the n. So m of these vectors, forming the columns of a matrix A. So I put them into a matrix. And the matrix then, so we have the length of the columns is n, we have m of them, so the matrix it's a zq n times m matrix. M rows, n rows, m columns. And we are asked to find a non-zero integer vector z whose length is at most beta, such that a times z, which is this expression here, evaluates to 0 mod q. That's all. So nq define the group we are working with. Here, beta is bound, and m is the number of elements we consider. Often this is also called a subset sum version, a vector subset sum, a modular vector-based subset sum problem. Right? Remember, subset sum, you are given integers, you are asked for subset of the integers that add up to 0 or add up to some specific value. And here we are given vectors. We are not just allowed here to pick 0, 1s, take a vector or not take a vector, but we are allowed to pick things here that are small. Together they are small. Okay. So that's it. So let's relate that. This doesn't seem to have anything in common with lattices, right? Well, there are vectors involved. That's good. There are integers, vectors involved. There are integer combinations. So maybe there are lattices involved, right? So, and that's what I want to explain first. But before I do that, let me say that here, I said on purpose, we are given m uniformly random vectors. So this problem is not a worst case problem. It's an average case problem. The inputs come from a certain distribution. So algorithms that solve this may actually have a hard time for certain specific instances or a certain set of instances if that set is small enough. Okay, so that it doesn't really matter. So when we say we want a good algorithm is one whose runtime averaged over the random instances. So it could be a probabilistic algorithm, then the runtime is an expectation over the randomness involved in the algorithm and over the choice of the inputs. Okay? That's important. Actually, why do we want something uniformly random? Well, cryptography is about randomness. These things usually are, later on, they will be sort of keys. They will be related to keys, and hence we need something that's sort of random. Okay, good. So far, so good. Now let's relate those things to lattices. And here is the relation. So again, we have n, m, and q. M is larger than n. And now we have a matrix as before in zqn times m. And given that, we define a lattice, which is called lambda perp of A, which is defined as the set of all m-dimensional integer vectors such that A times Z is equal to 0, mod q. Okay. A times Z. So what we're really asking for here is a short vector in this lattice for given A. Okay? You can easily see that, well, this is obviously a lattice. It's an R to the m, okay? And it's discrete. It's a subgroup, it's a group. If you add up two vectors that give 0, if you multiply them with A, then that's also true for the sum. Any integer multiplicative of them. And it's discrete. Well, it's discrete because it's a subset of Z to the m. That's here. Okay? And in fact, what we know, it's this thing is an m-dimensional lattice, and q times Z to the m. So vectors whose entries are all multiples of q are also in there. But if every entry of this is a multiple of q, then this is actually a 0 vector, modulo q, and then it gives you 0. Okay? Okay. And SIS NQ beta M is just the average case version of the shortest vector problem specified for these lattices. Average case in the sense that I pick a vector, a matrix uniformly at random from the set of all matrices of this form. And the set of A's that I'm looking at here is finite. There are q to the n times n many matrices, and hence there are q to the m times m at most that many lattices. There could be the same lattices. Obviously, if one matrix is a multiple of the other, then they define the same lattice. So they are actually fewer than q to the n times m, but it's the set of matrices is finite, so I can pick one matrix from this set uniformly at random. And then I just argue about the average case version of this. Okay? What's the nice property of these lattices in there? So you can view them as, or not view, but so look at the following picture. Here is q. Here is q. And here is minus q. Here is minus q. And here's 2q, 3q, and so on. Okay. Then you can partition the space here into these rectangles, right? to these, which partition the whole thing into boxes of side length q. Right? Okay. Good. Now, if you take a set of representatives for Z(m) modulo q, just all entries between 0 and q minus 1, say, then this defines a certain, a certain set in here, which looks hopefully pretty regular, okay? And then you can just translate that set here into this box, and it will look the same. You will have it there as well. Because if you add to this vector any vector that is in this set here, you will again get a vector in the lattice. Okay, so you translate this whole box here by q times z to the m. That maps this guy here to this guy here, and then everything's shifted up there. And the same is true here. You get it also in here, where you shift from here to here, so it goes this way, it goes this way, it goes this way, and so on. It goes also here, and it goes also here, right? So in all these things, these lattices look the same. So they have even more regular structures than lattices in general. Okay. And that's why they are called Q-ary lattices. They all look in each of these boxes. They look the same. In fact, these are all points in the lattice, obviously. Okay. And what is so nice about SIS is the following theorem that whose first version was shown by Miklos Aitai in 1996 and is considered the real breakthrough paper. And then it was improved in a series of papers, resulting finally in what I will probably mention at some point with the exact parameters. But two people that should be mentioned here is also Daniele Michancho and Odette Regev. And what they actually showed is that for any polynomial m in n, so any m larger than n that's a polynomial, and any, let me go back here first. Sorry, I forget something that I wanted to tell you. So do we have a solution for this problem? Do such things exist? And if so, for which values of beta do such things exist? Okay. What can we say about the bound, the best bounds that we can put in for beta such that we know that such a thing exists? Okay. Yeah. So as I stated here, it's not even obvious that a solution always exists. But our good old friend, the pigeonhole principle, will give us good bounds. And what I'll pick is so existence of solutions for SIS n q beta m. And so let m be strictly larger than n times log q. Beta may actually be a real number, I don't care. Okay? Yeah? And we look at the set S consisting of all 0, 1 vectors of length m. Yeah? then we know that S has size 2 to the m, which is strictly larger by this bound here than q to the n. Right? Log q goes to the into the 2 to the log q times n to the raised to the power of n. That's q to the n, right? However, for all z in z to the m, and in particular for all z in S, we know that a times z is an element of z to the q to the n. Okay? Which obviously has size q to the n. Okay? But this size here, this set here, has more elements than this here. Which means there must be two elements that map to the same vector here. Okay? This 0 here is a 0 vector. Yeah? So but this implies, I should say x is not equal to x prime, that a times x minus x prime is 0 mod q, and x minus x prime is not equal to 0 mod q. Okay? But this vector here, x minus x prime, since both vectors have only 0, 1 components, and if I subtract them, they are in minus 1, 0, 1 to the m. Which implies, well, the Euclidean norm of such a vector, well, each entry is at most an absolute value 1. So this implies that the length of this guy here is bounded by square root of m. Okay? So we conclude that if m is at least n times log q and beta is at least square root of m, then solution to SIS n, q, beta, m always exists. Okay. In particular, we can argue that, and that's true for all matrices in ZQ to the n times. I never used any property about the matrix itself. Well, except that it's in ZQ to the n times m. Yeah? So in particular, what we showed is that for all in A, Z, Q, N times M, we have that lambda 1 of capital lambda perp A is less than square root of M. Okay? Using heavier machinery, actually quite heavy machinery, depending on what bounds you want to get. You can even show that for most A's, lambda n of A is not much larger than square root of M. So they even have n linearly independent vectors, or m linearly independent vectors of length at most square root of M. But that's no longer true for all A, but for the overwhelming majority of them. So this is what I wanted to say about this. So we do have, by the Pigeonhole principle, we do have short solutions for this problem always. So such things always exist. But as you know, Pigeonhole principle doesn't give you a way of actually finding those things. Actually, there's a whole theory about this topic of Pigeonhole principle and finding solutions. So proofs by Pigeonhole principle, can you transform that into efficient algorithms? In general, we don't think that is true. If it did, then probably P would be equal to NP or something. Okay, good. So things exist, we have to find them. Now let's go back to how hard is this problem? Okay? This guy here. How hard is this problem? And it's an average case problem. And that's a notorious question in complexity theory and very much related to cryptography. Complexity theory traditionally and most successfully talks about worst case complexity, how hard it is in the worst case. But for cryptography, we need at least average case complexity. How hard is it for random instances? Because the instances are determined by keys in cryptography. And we want things to be hard for almost any key, and not just for 50% of the keys, so that in half of your e-banking transactions, somebody sneaked into this thing and channeled the money from not to your bank account, but to his own bank account. So that's not what we want to happen. Right? So, and that is the amazing power of this theorem that says this average case problem, SIS, is hard if certain variants of SVP and SIVP are hard. And these are all determined, which versions are all determined by these parameters N, M, Q, and beta. Okay? And it says that so this theorem, Aitai, Michancho, Regev, but other people were involved, also Neruka, Guy, and whatever. So for any M that's at least polynomial in N, and any beta and any sufficiently large Q, beta times some other polynomial in N. Sufficiently large means it's large enough to guarantee that a solution exists. That's the least that we need. Solving SIS N, Q, beta, M with non-negligible probability, so just significantly better than almost zero, is at least as hard as solving the decisional approximate shortest vector problem, gap SVP gamma, and the approximate shortest independent vectors problem, SIVP gamma, on arbitrary n-dimensional lattice with overwhelming probability. And for some gamma, that's also beta times polynomial n. And here is SIS is average case. Here, arbitrary. It's a worst case problem. Okay? So if these worst case problems are hard, then our SIS problem is even hard on average. Okay? And this gamma here, beta times poly n, you can, well, depending on what, the parameters won't be so interesting for us, although in practice they are interesting because they determine key sizes, stuff like that. But here it won't be so important. So here gap SVP and SIVP gamma. But these things, the parameters here don't guarantee that these things are NP hard. They probably, they in all likelihood are not. Okay. You know one other problem where we have such a worst case to average case reduction. These things are called worst case to average case reduction. So not average case to worst case, but worst case to average case. Because to show this, you show that if we want to solve this worst case problem, We reduce it to this average case problem. Okay? How did Itai ever come up with the idea that that should work? Well, he drew this picture here with an arbitrary lattice on top of it, went to the back of the room and realized, I can't even see a difference. Lattices, if you are far away, go far away, then they look as if they are the same in every of these boxes, if these boxes are also large enough. There is something that, yeah, there are errors, but if the box is large enough and you go far away, then these things you cannot hardly see that this is not regular within each box. It all happens around the boundary that there are some irregularities. Okay. These irregularities cause this poly-n factor here. You go from beta here, there, to beta times poly-n there. The real proofs are much harder than that. This was just the intuition that he claimed that led to this discovery. Good. It's the, okay, let me give you another problem where we know that this such a worst case to average case happens, and I will explain why this is much more interesting than this problem, and that's discrete logarithms. Okay? You want to solve the discrete logarithm, say, in a group ZP star. Now you have a generator. We know that this thing P is a prime. Right? Now I give you an element H, which is G to the A. And so this is given. Find H. Okay. Suppose you have an algorithm that does that for random instances, for H that are random from ZP star. Okay. I claim that that's good enough to solve it for every instance. Okay. So what you do is simple. You pick R uniformly at random from ZP minus 1. You set H prime to H to the R, which is G to the A times R. Everything's mod P. This now is a random element in ZP star. It's picked uniformly at random. Now, if you have an algorithm that with high probability is successful for random element in ZP star, it will be successful for this element. It gives you R times A. Once you have R times A, you divide by R. You get rid of the R. Okay. And you're done. Now, why was that so interesting when we already knew that such a thing exists for discrete logarithms? Well, the discrete logarithm problem is not considered to be that hard. It certainly is. Most people think that it's much, much easier than these things that are considered to be really difficult, although maybe not NP hard. Okay? Good. So these things, this was like the first one where we had any hope of proving that the problems really are difficult, even though they may not be NP hard. At the time that Itai proved this theorem, nothing was known about the hardness of SVP. So 2 years later, he proved that it's NP hard. Under random, in the exact version under randomized reductions, which is still the state. Randomized reductions means they make errors. Sometimes the reduction doesn't work, but that happens only with tiny probability. The other thing here is that I want to mention here, non-negligible probability. overwhelming probability. So if this is just needs to be successful on somewhat significant fraction, then you can do this for all lattices and with probability close to 1. There are no bad lattices. If you repeat the process, then you can boost this obviously to anything you want, very, very close to 1. Okay. Yeah. Keep this in mind. I will come back to it later and relate it to collision-resistant hash functions. So that's why I also said this. For each matrix A, I have here a function, right? Fa of z that is defined on z to the m. Maps z to the m to some vector in zq to the zqn. Or maps anything from this domain here to an element in zq to the n. And then you'll see that collisions correspond to short solutions. So if it's hard to find short solutions, it's hard to find collisions. Okay, but it turns out that SIS has many applications in crypto, but it's mostly used to construct signature schemes and hash functions and certain one-way functions, stuff like that. But it's typically it's much harder to get encryption schemes than signature schemes. If you went to the course on foundations of cryptography, you may remember, okay, or if you don't remember it, I just stated, signature schemes, secure signature schemes can be constructed once one-way functions exist, period. So signature schemes, which are a public key primitive, exist if one-way functions exist, if and only if one-way functions exist, and one-way function exists if and only if private key, secure private key encryption schemes exist. We have no idea how to construct public key encryption schemes from just one-way functions. For that, we need so-called trapdoor permutations or trapdoor functions, which is a much richer structure. And in fact, we think that really, it may be the case that one-way, we think that one-way functions and trapdoor permutations exist, but those things are probably independent, or they are independent. There are worlds, not our universe, but a different universe, where one-way functions exist, but trapdoor permutations do not exist. If you went to complexity theory, you look at oracles, and you look at relativized worlds, and there are things with. Okay, anyway, so SIS can lead to efficient, as we all see, efficient and nice signature schemes, but it's not good to really come up with encryption schemes. And if you want encryption schemes with more functionality, which is identity-based encryption, attribute-based encryption, predicate encryption, or even the holy grail of modern cryptography, homomorphic encryption, you need something else. Okay? And that's also, these are all topics in the course, in the seminar. So we need a different problem for that, and that goes back to Oded Regev. And for this problem, this paper in which he introduced this problem, he actually won the Gödel Prize. So this is really an amazing thing. I will come back to that later. And this is the so-called learning with errors problem. Okay. In the learning with errors problem, again, we have the parameters n and q play a similar role than n and q before. And in addition to that, we have a distribution on Z, on the integers. So distribution that assigns to every element in Z a certain weight or a certain probability. Here it's really a probability. It's not a mass function because these are discrete probabilities. And chi on every element in Z is non-negative, and they all sum up to 1. So as an infinite series, these values sum up to 1. In fact, later we will specify chi to be a certain Gaussian distribution, a discrete Gaussian distribution, with parameter, as they is usually called, or standard deviation alpha times q for some alpha that's less than 1. Okay. Standard deviation, you hopefully remember, standard deviation always says you have a distribution, you have the expectation, and to get a constant probability for some event, so say centered around the expectation, you always need at least a few standard deviations around the expectation to get constant probability of ending up in that interval. Yeah? That's standard deviation. Yeah? Good. Okay. And this is also called often the error rate, as we'll see. Moving too much? So, and then we'll define the LWE distribution. And for that, we'll fix a vector S in ZQ to the N. And it's called the secret. And the LWE distribution, AS comma chi, S, this vector, chi, the distribution from there, over, so it's a distribution on a finite set. The finite set, ZQ to the N times ZQ, so ZQ to the N plus 1. But there's a reason why I write it this way. And the distribution is defined by picking a vector uniformly at random from this set here, ZQ to the N, and also choosing an element E from the distribution chi, so E is an integer, and outputting A and B, where B is the inner product of A and S, hence S has also to be from ZQ to the N. But I interpret this as a natural number and add this E to it. So this is an integer, inner product, and I add E, mod Q. Okay. So what you do here is basically, can I erase this? Yes, well, no. I can erase this here. So you, so A times S means, so it's like sum of the A or AI times SI. So it's kind of like a linear equation. But then I add an error term, this E. Okay? Or if I collect all these things, if I have many of those things and collect them into a matrix, as we'll do later, then we have like a matrix times this S. But I don't give you the result of that multiplication. I sort of manipulate it a little bit, transform it by adding this error. Okay? Term. That's the LWE distribution. And then you can see that here, and how is this, I won't, for the time being, I won't describe what this chi is actually going to be. Here you can see that if I make alpha smaller and smaller and smaller, Okay, then what's going to happen is that 0 or small values get a larger and larger probability. Yeah? So this error becomes smaller and smaller and smaller. And what I get here is closer and closer to the truth, which is this. Yeah? Okay. And this is very much related to error correcting codes and error correction, where an error correcting code does exactly this. So instead of sending a message M, it sends many of these things here. And then in transmission, you have errors. And then you try to recover the original message back from the erroneous message, the received message. Okay. Yeah. Good. Yeah. And now we want to define problems for it. The first one is a search problem. Search LW N Q chi M. Again, so SIS was NQ beta M, so I place one Greek letter for another one. So this beta now is a chi, it's no longer a bound, it's a distribution. So given M independent samples drawn from this distribution, independent means for every sample, I pick AI independently from all the other things. But the S is fixed in all these samples, and also the error E is picked independently from the other errors. Yeah. Given that, find S. Find the vector S. Yeah. If I did not have this error in there, if I give you roughly n plus 5 samples, you can recover S. Because with n plus 5 samples, the probability that there are n things that are linearly independent, n AIs that are linearly independent, is large. And given that, you can even identify those. Well, you can see which ones are linearly independent. You pick them, invert Gaussian inversion, Gauss algorithm, and you recover S. Okay? But here I introduce this error. Okay? And with this error, Gauss doesn't work. Well, variants of Gauss work, but it needs time 2 to the n. You sort of try many, many, many subsets until you find something that satisfies all your constraints. Okay? That's actually one of the topics in the seminar, an improved version of this algorithm, or an improved approach to this algorithm in certain cases. There's also, which is not part of the seminar, I think, Bloom-Wassermann. I didn't pick that, right? There is this algorithm by Bloom-Wassermann that solves this problem in time 2 to the n divided by log n. So n divided by log n is in the exponent. It's the best that's known for this problem. Okay. Okay. So that's the search version. You have to search for the S that's behind it. Okay. If you have heard about cryptography, you have seen that many of our cryptographic security definitions relate to or are based on distinguishing things. Distinguishing, say, if you want to, what happens if you always pick message M0 versus picking message M1? Having a truly random function versus a pseudo-random function. Having a random bit string versus a pseudo-random bit string. Okay? And so it seems natural for this thing here to also define, we have already a distribution here, so why not define a decisional version or a distributional version, and that's what we do here. So given m independent samples ai, b in the appropriate range drawn from either our distribution A S chi for a uniformly random S, which is fixed for all samples. So this is one world in which you may live. The other one is you pick the uniform distribution here. Okay. You have to decide in which world do you live. You get samples from either one, and you have to decide which is the case. I don't want to go into the formality, but you look for adversaries B, say, and the probability that they output 1, if they get something distributed according to this, should be negligibly close to the probability of outputting 1 in this case. Okay. And again, if I choose here my alpha to be 1, okay, alpha is 1. So the parameter is, the standard deviation is Q. Then what you get here is basically a uniform random element from ZQ. It's not quite that, but close to it. In which case, there's no way you can distinguish these two cases because they are the same. In fact, you can show that in that case, the statistical distance between these two distributions is small. So small that nobody can distinguish it. Not even if you have infinite power. If I don't limit you to polynomial time or so. So this here really is less than 1 is important. The smaller you make alpha, the more concentrated your errors are around 0. So the farther apart mathematically these two distributions should be. If I make it 0, then you can distinguish. Even if you make it slightly, you can easily show if it's slightly above 0, you can still distinguish. Okay. Most of your errors will be 0. So because 0 or 1 in the standard deviation. So I make alpha to be 1 over Q. Almost everything 0. If I pick it according to chi, if it's 1 over 2, if it's 2 over Q or something, it's still mostly 0s, 1s, and 2s. Doesn't really hurt. Okay. So, and what we usually do is we combine these samples into a matrix A, which is ZQ to the n times m. Okay. And then what I get here, I write that in a matrix form. So what we get is here A times S transposed, because S is also an n-dimensional vector. So if the way this here, you can also write as S transpose, which is now a row vector, times a column vector, which is a number. And if you do that for all rows, you get exactly this thing here. And you add a row vector. Now what you get if you S transposed is in, so S transpose is in Z1 to the n, you multiply it, A is in ZQ to the n times m, then S transpose times A is in, well, you ignore the middle part, right? Is in 1 times m, which means it's a row vector. One row, but I usually want to deal with When I write this E, it's a column vector. If I don't say anything, things are always column vectors. So that's why I have a transpose here. Okay. I could also write this as A transpose times S, which gives me a column vector. Then I don't need it to do here a transpose. You will see all kinds of versions, and sometimes it's easier to do one thing or the other. Yeah. But that's actually what we do. Sometimes people even say the matrix A is this matrix here plus this guy here as an additional row. You just, or yeah, this thing here as an additional row. All matter of personal taste. But since people have different tastes, in different papers, they do different notations, and it's just meant to confuse us. Yeah. Good. Yeah. Are there any lattices involved? Yep. Again, quinary lattices. This time we have n, m, q, and n, with m is larger than n. We have this alpha, a, it's in here. And now I define a new lattice. And just to confuse you, I rewrote everything with the transpose on the other side. Never mind. Turns out that this other version is better for some other things. So lambda A is all vectors of the form A transpose times S, where S is in ZQ to the N. And I add Q times Z to the M. And that's a lattice. Because if you have two things in here in that set, well, for each one there is an S1 and S2, and so also for the addition there's S1 plus S2 that also leads to that combination. Okay, and to make it a real lattice, an infinite thing, I add this stuff here. Right? And again, this part is in here, and again, it's the same picture, right? I have this part here. That's my green stuff here, in here. And then I add Q times lambda, Z to the M. So I copy that part into all of my boxes here, which gives me a lattice. And then LWN, chi, N, Q, chi, M can be viewed as an average case version of BDD, bounded distance decoding. Because what I get here is not, this here is an element with transpose, is an element in my lattice. But I add an error. I move it away from the lattice by adding this error term. Okay? So this part gives me a lattice point, something in here, but then I add this error and I move it away from the lattice. And then obviously I want to recover in LW the lattice point. And if E is small enough in length, then this is actually BDD, bounded distance decoding. And hopefully we should make things so small that the error is so small that with high probability there's a unique lattice vector that is closest to it. Yeah. So that's why, again, we have Q-ary lattices. And these things here, so you will find in many papers, you will find this lattice, and you will also find this lambda perp lattice. So this here is, in terms of, if you want to think of linear algebra, lambda of A is the image of A, but considered as a subset in Z. Okay? Lambda perp is the kernel of A, considered as a set in Z to the M. Okay? Why it's called perpendicular. If you look at the other thing, they should be modulo Q perpendicular to all rows. 0 mod Q. That's why it's called lambda perp. Okay, what do we know about this and its hardness? This is a frightening looking theorem, but it's not quite as bad as it looks. So for any m that's polynomial in n, and forget about this beta, it's copy and paste, delete it. And any q that is at most exponential in n, and any discretized Gaussian error distribution of parameter alpha q must be at least 2 times square root n. So the standard deviation is not allowed to be too small. Yeah? At least 2 times square root of n. Solving the decisional LWE problem NQ chi m is at least as hard as, and now comes the thing, quantumly solving gap SVP gamma or gap SIV gamma on, again, arbitrary n-dimensional lattices with overwhelming probability, and for some gamma, which is O tilde n divided by alpha. Tilde here, there are some polylog terms involved. So some log to something of n. Okay? So, but it's again the same thing. We saw that this guy here is an average case version of BDD, and here we relate it to worst case problems. Okay? Yeah? Here's a quantum algorithm involved. Okay? So the reduction is a quantum reduction. It uses really quantum mechanical things. You can get rid of this quantum here, but then this here says Q is not allowed to be too large. If you want to get rid of the quantum in there, that's due to Chris Picard himself, then Q must be at least 2 to the n. So you need large moduli for getting rid of the quantum reduction. Okay? As we'll see, this Q should not be, for practical purposes, it should not be too large. Because if it's getting large, then our keys will get larger and larger. So it really, we would like to have Q to be n squared, for example. 2 times n squared. Something like that. And if you want to get rid of this quantum stuff, that is not known to be true. It's also not known not to be true. So, which are two different things. Let's do a little sanity check. The relation of these things here, right? How alpha appears here and alpha appears here. Okay? If you make alpha smaller and smaller, LWE gets easier and easier because your errors get smaller and smaller. Yeah? If you have smaller errors, bounded distance decoding should become easier. Right? You have small errors. If the error is 0, it's easy. So if alpha gets smaller, the thing becomes easier and easier. So I should be able to relate or reduce problems to it that become easier and easier as well. Right? And that's here because here it's 1 over alpha, so as alpha gets smaller and smaller, the approximation factor that I allow gets larger and larger. And with increasing approximation factor, obviously such approximation problems become easier. Right? You have more space to work with. Yeah? So that's how you can always remember these things. And we can never, here you can see that alpha is sort of, alpha is at least square root 2 times n divided by q, something like that. If you think of q, which will be a common thing to do in all the papers that you look at, is alpha q to be roughly n squared. Okay. Then q is n squared, then alpha must be at least 1 over n to the 2/3. Okay? 1 over n to the 2/3. So that's what you can get here then is n times n over 2/3, so n to the 5 divided by 2. Okay? Which is again much larger than n, well, it's larger than n or square root of n. So we don't know that for these problems these things are NP hard. In fact, we don't believe that they are NP hard, but we can still hope that they are hard. Even if they are not NP hard. Okay? Okay. Gamma is M and gamma are mostly M and Q are mostly irrelevant here. Okay. Questions about this? Questions? Also, they can only see the video. They cannot ask questions, right?
Because they aren't.
Nobody's there. Okay.
Well, people out there.
Okay. I promise you to go to cryptographic things. I will do that briefly only for hash function collision resistance and see how this relates. Just make this more formal, what I already told you. Okay. And that I'll do. This is. So that's the next part of this series of lectures, cryptographic primitives and security notions that we'll work with. I don't present everything. Okay, and we'll mostly, well, we only deal with public key primitives, which usually means that definitions become harder. And the first thing that I need is cryptographic hash functions, function families. Most of the things that we'll be dealing with can be phrased in terms of function families or similar things, although they may lie in the back of the whole thing. I will only present the security notions for encryption schemes, hash functions, and signature schemes. In your essays and in your talks, you'll talk about other things as well, like IBE, identity-based encryption, attribute-based encryption, and stuff. So you can see this is kind of the abstraction level that you can use for your definitions as well. Okay. But I do the easy stuff. The hard stuff is for you to do. So a function family is an index set of functions. So this function, the set is called F, and we have a key space or index space, capital K, and for each element in K, we have a function Fk with its potentially own domain and range. So each thing determines a domain and a range, domain xk and yk. Example. Yeah, let's do a simple example, and then we'll do something harder. So I could say that in my example, the key space is even finite. And it's ZQ to the n. And say if I have an A in ZQ to the n, I have a function Fa. And okay, maybe I also have, sorry. I want something like this. ZQ to the n times m. Q and m are certain parameters. And then this thing here simply A times Z goes from say ZQ to the m to ZQ to the m, and it maps x to A times x modulo q. This is usually not what I don't want to deal with that later on. I'll just use a different domain. Okay. Now you can imagine I can say that I look at all keys k where here and where n, m, and m are related in some way. Okay. So I can also extend that to k is the union over all z, q, n times m, and this union is over all n, q, comma m, where n is in n, but say q, m determined in some way. Okay? So for example, I could say you can pick any n in n, but then m has to be n times log q rounded up, and q has to be n squared. Okay? Then you have an infinite function family. Yeah? So there are functions from q is a function of n, m is a function of n, or of nmq, whatever you want. Yeah? These need not even be finite sets, but in our cases they usually are finite sets. And if we say that the size of yk is always less than xk, then we say that fk or f compresses its inputs. And then we call f a hash function. Function and function family often are the same. Often, but not always, k is a subset of 0, 1 star. Well, in this case, it's a subset of 0, 1 star. You represent everything in binary, and then you have a relation between certain parts. So that's really not a restriction. And often there are also polynomials d and r from n to n, such that for all keys k in the set of keys, xk is determined by the length of k and the polynomial d, and yk is also 0, 1 to the r of the length of k. Again, you can interpret obviously this here, m. This has obviously this property, and this you can also here. You just give yourself a little bit more space so that you can every element in here can be represented by a bit string of that length. Just doesn't really matter, but this is often the case, but I prefer usually to have a much more precise and mathematical, meaningful definition. I skip that. So collision resistance. A family F is collision resistant if F is easy to evaluate on all inputs, which means there is a polynomial time algorithm. I give it the index k, I give it the input, and it evaluates the polynomial time, the function family with that index on that input. what's written down here after the semicolon, and over the internal random choices array. This is mostly the standard notation these days.
Jetzt kurz dein Mikro checken. Ist noch an?
Nee.
Okay. Kannst du mal Zoom mal anzumachen? Unten ist Knopf, glaube ich. Ah, ist ziemlich leer. Okay. Ja, versuch mal.
Okay, and then it has to survive one more sentence. If you look at this board and at this part here, you see that this thing here, the FAs that I defined, define the function family, and what we can is that if these lattice problems are hard in the worst case, then these things are collision resistant. It's a collision resistant hash function with certain parameters. That really uses this domain. Next time I will tell you it's also a one-way function, but that's based on some other problem that's equivalent to SIS. It's the inhomogeneous version of SIS. But that's equivalent. You don't have to find a vector such that A times Z is 0, or you have to find A times Z is some other vector U. Inhomogeneous. That's not so good. And then for the pre-image, it's hard one way. Good. And then next time we'll go to the harder things, signatures and encryption schemes, and then I'll introduce chapters. Chapters are the important ingredient for public key encryption schemes. And we'll introduce lattice chapters, two different ways of defining chapters for lattice. And that's it for today. Is that?
Yep.
I could go on with the microphone.
Sure.
Good. Okay, thanks.